Okay, so imagine you're working on a shared doc with three of your friends. You make a change. Do they see it right away? What happens if you all make changes at the exact same time? Whose version is the real one? This, right here, is one of the biggest headaches in distributed systems. And the solution? Well, it's found in something called consistency models.
So to make this super clear, we're going to use one simple setup for this whole explainer. Let's meet the players. We've got four processes, P1, P2, P3, and P4. Just think of them as four different computers. And all they care about is this one piece of shared data, a variable called x, which right now is just chilling out at a value of 0. This is going to be our stage.
And this brings us to the big question, right? If P1 decides to change that data, do the others see it happen instantly? Do they all see the same updates in the same order? The set of rules a system follows to answer these questions, that's its consistency model. It's basically the contract that says, here's when and how you get to see the latest truth. Let's kick things off with the gold standard. This is the one that works exactly like your gut tells you it should. It's called Linearizable Consistency, and you can just think of it as a perfect, instantly synced world. Okay, so watch our timeline. P1 makes a change. It writes a new value. X is now 10. In a linearizable system, the very instant that write is done, bam! It's like the new value is broadcast to the entire universe. Every other process, P2, P3, P4, if they try to read X from that moment on, they will see 10. No delay, no confusion. So what's amazing about this is it makes a whole network of computers feel like one single predictable machine. There's one official timeline of events that everyone agrees on. It's super easy to reason about. But, and this is a big but, making this perfect sync happen in the real world is really, really hard. And often, it's pretty slow. It's the dream, but it's an expensive dream. Okay, but what if that instant, real-time guarantee is just too slow for what we need? What happens if we decide to relax the rules just a little bit? Well, that brings us to our next model, FIFO Consistency. So now, watch P1, it goes on a little writing spree. First, it sets X to 1, then to 2, and then to 3. Now, FIFO consistency makes one simple promise. Every other process will see P1's updates in that exact order. They'll always see 1 before 2 and 2 before 3. The order is sacred. But the timing, yeah, that's not guaranteed anymore. And here's the trade-off, right? We're guaranteeing that all the writes from one process stay in order for everyone. But that idea of a single global timeline, it's gone. P3 might see updates from P1 and P2 in a different order than P4 does. So we've sacrificed that global time for better performance, while still keeping things from getting totally chaotic. So far, the system has been in charge, enforcing these rules automatically. But what if we, the developers, want to grab the steering wheel? What if we want to be the ones who decide when data gets synchronized? This is where we get into weak consistency. And the rule here is, well, there are no rules by default. A process can change its own local copy of the data all at once, and the rest of the system might be totally oblivious. Until the programmer steps in and says, okay, time for everyone to get on the same page. And that's called a synchronization. Check this out. P1 changes X to 50, but look at P2, P3, and P4. They're still living in the past, seeing X as 0. They have no idea anything has changed. Then a sync operation is called. It's like a system-wide fire alarm. And just like that, all those pending updates get flushed out and everyone's view snaps to the new reality. X is 50. Now, a global sync is a bit of a sledgehammer. We can be way more precise using a pair of actions, release and acquire. Here's an easy way to think about it. You're writing in a library book. When you're done, you release it back to the shelf for others. Then, when someone else wants to read it, they acquire it, which guarantees they're getting the version you just finished with. So look here, P1 updates X to 100 and then performs a release. That's P1 basically shouting, hey, my updates are ready for you. Now, over on P2's timeline, it knows it needs fresh data, so it performs an acquire. And only after that acquire is complete can it be sure that it will see the value of 100 that P1 released. It's a very clear, direct handshake between the processes. But what if we need to be even more surgical? That's where entry consistency shines. Let's say we have two variables now, X and Y. P1 only updates X. Now, P2 doesn't need to sync everything. It can specifically say, I only care about X right now. It acquires a lock just on X. And the result? P2 sees the new value for X, but its local view of Y is totally untouched. This is the ultimate in fine-grained control. All right, that was a pretty fast tour through 5 very different ways of looking at data. Let's pull it all together now and put them head-to-head in a final showdown. You know, before we get into a formal chart, I've got a little analogy for you. Consistency models are basically just like group chats. Seriously, linearizable is that perfect chat where everyone sees your message the second you hit send. FIFO is when you know your one friend's messages will always show up in order. And weak consistency, that's when you have to keep pulling down to refresh the app just to see if you missed anything. And this table right here, this is your exam cheat sheet. It lays it all out. Linearizable, you see the latest value instantly. FIFO, you see P1's writes in order. Weak, you're stuck with the old value until a global sync. Release, you only get the new value after you acquire it. In entry, only the specific thing you ask for gets updated. It all maps perfectly to our group chat world. Okay, let's switch gears. For all of you staring down an exam, let's talk strategy. How do you take all this stuff we just talked about and turn it into full marks on a test? Here's the secret. Don't just write a big block of text. Draw it. Start with those 4 parallel timelines we've been using this whole time. Show the write happening on P1. Then, and this is the key part, use arrows and markers to visually show exactly when P2, P3, and P4 see that update based on the rules of that specific model. And then just add one sentence underneath that says why it happened that way. Show them, don't just tell them. You know, when you really boil it all down, it comes back to this one idea. In any complex system, you can have a single source of truth, the same data. But at any one moment, you can have many different, equally valid views of that truth. And that's their job. Consistency models are the rules that manage all those different views. They define what correct even means. And they always represent a trade-off between being super strict and being super fast. Choosing the right one, it's not just a small detail. It's a huge decision that defines how your entire system is going to behave. And that is what consistency models decide.